Determining the masses of stars. Many of the stars in the sky are actually binary stars in which two stars orbit around about their common center of mass. So two stars orbiting about their common center of mass. If the orbital speeds of the stars are high enough, the motion of the stars can be detected by the Doppler shifts to the light they emit. So these stars emit light, and we measure the Doppler shift in the detected frequency of the light. Stars for which this is the case are called spectroscopic binary stars. Figure shows the simplest case of a spectroscopic binary star, two identical stars, each with mass m, orbiting their center of mass in a circle of radius capital R. The plane of the star's orbit is edge-on to the line of sight of an observer on the Earth. So this is edge-on with the line of sight of the observer on Earth. Okay, so in order to answer this question, we have a source of light that is moving at a high speed. We have to use relativistic Doppler effect. So let's think about the relativistic Doppler effect. We have a moving source that emits waves of frequency f0. So first wave crest is emitted here, and source emits the second wave crest at this point. And position of the first wave crest at the instant that the second crest is emitted is at a distance speed of light times the period of the emissions as detected by the stationary observer. And also the wavelength is the distance between the two crests, because the star is moving with respect to the observer with a relative speed u. The source of the wave has moved a distance u times t when it emits the second crest. So therefore, the wavelength that is detected by the stationary observer will be c capital T minus u capital T, where u capital T is the period determined by the stationary observer. Okay, so the stationary observer detects waves of frequency greater than their actual frequency. Alright, so a source of light approaches a stationary observer with constant speed u. In the source reference frame, light is emitted with frequency f0. So f0 is related to the period of the emissions. f0 is equal to 1 over the period, where t0, the period, is determined by the source reference frame. So what is the frequency detected by the stationary observer? So as we just argued, the detected wavelength lambda is the distance the first crest travels, c times capital T, minus the distance the source travels, u times capital T, when it emits the second crest. So this t is the measured period. So what is the detected frequency? Detected frequency, the speed of light is c in all reference frames. It's c divided by the detected wavelength lambda. So it's going to be equal to c divided by c minus u times the period of the emissions detected by the stationary observer. Now, who is measuring the proper time for a periodic event here? The proper time is measured in the source reference frame, because each crest emission process in the source reference frame happens in the same position in the source reference frame, so it measures the proper time t0. In the stationary observer reference frame, we have time dilation, so the period detected by the stationary observer will be relativistic correction factor gamma times t0. So this is the proper time t0 divided by 1 minus u square over c square square root. Okay, so if I write this with the common denominator, c square minus u square over c square, inside the square root that becomes c and goes upstairs. So this can be written as c times t0 divided by c square minus u square square root. Okay. Now, then what is the detected frequency? Detected frequency is c over c minus u parentheses times t. So it is c over c minus u. And I have 1 over t here. So 1 over t, it's going to be c squared minus u squared can be written as c minus u times c plus u inside the square root and divided by c times t0. So you can see that these c's will cancel and I will have for this frequency one over t0 times, because square root of c minus u can be written as c minus u squared inside the square root. I'm going to get rid of one of these c minus u's here. So this will give me 1 over t0 square root of c plus u divided by square root of c minus u. Now what is 1 over t0? Remember, 1 over t0 is the actual frequency in the source reference frame. It is 1 over t0 is f0. So we can write the detected frequency as 1 over t0 times, which is f0 times, square root c plus u divided by square root c minus u, for which scenario? This is when the source is moving toward the observer, the stationary observer. And if the source is moving away from the observer, this minus sign, this plus sign and minus sign will change. So we're going to replace it by minus and plus. There's going to be a decrease in the frequency. It is c minus u square root divided by c plus u square root. And when does this happen? When the source is moving away from the observer. So these are relativistic Doppler shift formulas for the case when source is moving towards a stationary observer with relative speed u, or moving away from the stationary observer with relative speed u. So this is basically our relativistic Doppler effect. And that's what we need to use in order to calculate the detected frequencies for this for the frequency of the light emitted by these two binary stars as seen by a stationary observer on Earth.